Good day, viewers. Today we are going to be learning how to prove some relations under Joule-Thomson coefficient. So Joule-Thomson coefficient describes is nothing but describing the relationship of how temperature changes during an adiabatic process at constant enthalpy. So Joule-Thomson coefficient, we said that mu, which is denoted by mu, is nothing but the partial derivative of t all over the partial derivative of p, keeping h, like I said earlier, which is enthalpy, constant. So next, we are going to be relating Cp. We know that Cp and mu are related to P, they are related to P, T, and H. And from our cyclic relation in our previous video, on cyclic relation, we made a relation for P, V, and T. So here we are going to be expressing this relation in terms of P, T, and H. So what we are going to be having here is the partial differentiation of these three terms, just like how we did for our cyclic relation. So we are going to be having, this is nothing but the partial derivative of H all over the partial derivative of P, keeping T constant, multiplied by the partial derivative of P all over the partial derivative of T, keeping H constant, multiplying the partial derivative of T all over the partial derivative of H, P constant, is equals to -1. So this is what we have. So next, we are going to be making the partial derivative of H all over the partial derivative of T, keeping T constant, of P rather, keeping T constant, the subject of this relation. If we do that by dividing both sides of this equation, we are going to have the H all over the P of T all over the H all over the P of T multiplied by the P all over the T of H derivative of P all over the partial derivative of T, keeping H constant, multiplied by the partial derivative of T all over the partial derivative of H, keeping P constant. We are going to be dividing by this and also dividing -1 by this also. So we say the partial derivative of keeping H constant into the bracket, we go with this. So we'll be left with the partial derivative of H all over the partial derivative of P, keeping T constant, to -1 all over the bracket of the partial derivative of P all over the partial derivative of T, H of T rather, all over the partial derivative of H, keeping P constant. This is what we have. So if we take the inverse of this, we are going to be having the partial derivative of H over the partial derivative of T, keeping P constant, to be equal to minus, we take the inverse of this, this will become the partial derivative of T instead of the partial derivative of P all over the partial derivative of P, keeping H constant, into the partial derivative of H over the partial derivative of T, keeping P constant. Mu, which is equal to Joule-Thomson coefficient, is equal to the partial derivative of T all over the partial derivative of P, keeping H constant. We know this, and we also know that the partial derivative of H is equal to Cp, the partial derivative of T. So we can decide to make Cp the subject of this relation. We are going to have, by dividing both sides by the partial derivative of T, we are going to have Cp to be equal to, this implies that Cp will be equal to the partial derivative of H all over the partial derivative of T, keeping P constant. So if we do this, this is what we have. So we now, for this equation, we are going to be substituting mu for the partial derivative of t all over the partial derivative of p, keeping h constant, and we are going to be substituting cv for the partial derivative of h all over the partial derivative of t, keeping p constant. It will become minus mu cp. So we have just substituted the value of mu and cp in this equation. So now we know that from our second TDS equation, we know that TDS is equal to Cp dt. TDS is equal to Cp dt minus t into dv, that is the partial derivative of v over the partial derivative of t, keeping p constant. This is what we have from our first TDS equation. This is what we have. So next, we also know, so this is what we have as our TDS equation. You can find the proving of this equation from our previous videos. So next, we also know that TDS, from our laws of thermodynamics, we have derived a relationship that shows that TDS is equal to dH minus V dP. You can also find this from our previous videos. Now, equating these two equations, if we equate these two equations, we are going to have in dH minus V dP to be equal to dP dt minus t into dV all over dP. So this is what we are going to be having. So next, we are going to take minus VDP to the other side of this equation. If we do that, we are going to have the H to be equal to P. So this is what we have. So we have the P here, we also have the P here. So we are going to be factoring out the P. So if we do that, the H will be equal to the P dt into the bracket partial derivative of v over the partial derivative of t, keeping p constant, close our bracket, the p. So we have just factored out the p from these two terms here. So next, we are going to be dividing both sides. But before we do that, we know that from the definition of Joule-Thomson equation, Joule-Thomson coefficient, we know that enthalpy, which is H, is equal to 0. That is constant. So if we put the H to be equal to 0 in this equation, we are going to be having 0 to be equal to Cp dt plus the bracket of V minus T into dV dt, that is the partial derivative of V all over the partial dt. So this is what we have. So next, we are going to be taking Cp dt to the other side of this equation. If we do that, we will have minus Cp dt to be equal to the bracket of V minus T into the partial derivative of V all over the partial derivative of T, keeping P constant, the close bracket dP. Have the P. So this is what we have. So next, we are going to be multiplying both sides of this equation by minus. If we do that, we are going to have Cp dt, minus times minus is plus, will be equal to minus V, that is the bracket of minus V plus T into the partial derivative of V all over the partial derivative of T, keeping P constant, close bracket the P. So this is what we have. So next, I will be writing this equation here. So we have Cp, dt is equal to the bracket of minus V plus T into the partial derivative of V over the partial derivative of T, keeping P constant, dP. So this is what we have. So in this equation, we are going to be dividing both sides by dt. We are going to be dividing both sides by dp cp. We are going to be dividing both sides by dp cp. So if we divide both sides by dp cp, we said the h will be equal to 0. So if the h is equal to 0, it means that for this equation, change in enthalpy is constant. So we can as well say that the Cp over the P, indicating that H, which is enthalpy, is constant. We can also do that here by saying H is constant and also adding a bracket here, signifying that H is constant because we substituted 0 for the H, meaning that H is constant in this equation. So next, we are going to be dividing both sides of this equation by Cp dP. To do that, we are going to have Cp dt all over H, that is H kept constant, all over Cp dt, keeping H constant, to be equal to minus V plus T into the partial derivative of V over the partial derivative of T, keeping P constant, the P, be closing the bracket, keeping H constant. So this is what we have. So in this equation, all over we have Cp dt, keeping H constant. So from here, we can have Cp goes with Cp, we'll be left with dt all over dp, we'll be left with dt all over dp, keeping H constant. That's what we'll be having. So we'll be having this, we'll be dividing this. So next, we're going to be having the partial derivative of t now all over the partial derivative of p, whereby we have H to be constant. This is what we have. It will be equal to, this is H constant, it will be equal to minus the bracket of minus V plus T into the partial derivative of V over the partial derivative of T, keeping P constant, the P, have the P here. This will be multiplying 1. If we take the inverse of this, if we bring this here and convert it to multiplication, we'll be having 1 all over Cp dt. So this will be nothing but multiplying 1 all over Cp dp, keeping H constant. So here we have P here, from here, this is P. So next, from this place, we can say that the P, we cancel out the P. So what we'll be having left will be dt all over dp, keeping H constant, to be equal to the bracket of minus V plus T dV all over the T of P. This is what we have, keeping H constant, T P. what we have. So here is going to be 1 because we have 1 all over Cp dp. So if dp goes with dp, we are going to be left with 1 all over Cp. So here we are going to have 1 all over Cp. So this is what we have. So now we can rewrite this equation by saying the partial derivative of t all over the partial derivative of p, keeping h constant, is equal to 1 all over Cp. It will be equal to 1 all over Cp, the bracket of minus, or we can rewrite this equation in the form of, we can say plus, that is t into the partial derivative of v all over the partial derivative of t, keeping p constant first before minus v. So we have t into the partial derivative of v all over the partial derivative of t, keeping p constant, minus v, close the bracket, keeping h constant. So this is what we have. So we know that the t all over the p, keeping h constant, is Joule-Thomson coefficient. So we can rewrite this equation as, since we know that mu, which is Joule-Thomson coefficient, is equals to this, which is the partial derivative of t over the partial derivative of p, keeping h constant, we can substitute for the partial derivative of t over the partial derivative of p, keeping h constant in this equation. So it implies that this equation will become mu will be equal to 1 all over Cp constant. This is what we have. Now from this equation, we can see that we have temperature. From this equation, we have temperature. So we are going to be relating Joule-Thomson equation, Joule-Thomson coefficient rather, in terms of an ideal gas. We are going to be relating it with an ideal gas to see if temperature will remain constant. So we'll be relating Joule-Thomson equation. So I'll be writing this equation as mu. This equation will be nothing but mu this equation down here as mu is equals to 1 over Cp into T. This is what we have. This is what we have. So now for an ideal gas, we know that PV equals to RT for an ideal gas. If we make P the subject of this relation, we are going to be having the subject of this relation, we are going to be having V to be equal to RT all over P. So this is what we have. We can as well make V over T the subject of this relation. If we do that, V over T will be equal to R over P. So if we differentiate this with respect to T, we are going to be having the partial derivative of V over the partial derivative of T, keeping P constant, to be equals to R all over P. So this is what we have. So coming back to this equation, we have the partial derivative of T over the partial derivative of V over the partial derivative of T, keeping P constant, to be equals to R over P. So we substitute the value of this in this equation. We are going to have mu to be equal to 1 all over Cp into the bracket of T, the partial derivative of V over the partial derivative of T. Now we are going to be putting R over P instead of this. So we are going to have T into R over P minus v close bracket. So we're just going to have just one bracket. So this is what we have, whereby we have h to be constant. So this is what we have. So next, from this equation, we can see that from here we can see that r over p is equal to v over t. R over p is equal to v over t. So we can substitute r over p we can substitute v over t for r over p in this equation. It means that mu instead of r over t. So we have v over t minus v close bracket, keeping h constant. Keeping h constant. So this is what we have. So next, we know that this is t and this is t. So t can cancel out t. We'll be left with mu equal to 1 all over Cp v minus v. Have left is mu equal to 1 all over Cp into v minus v. And we know that from here we have v minus v, which can be equals to 0. So definitely we can rewrite this equation to be, rewrite this equation to be mu is equal to 1 all over Cp into v minus v equals 0. So we can see now that Joule-Thomson coefficient for an ideal gas will be equal to 0. That is, there is no temperature change. So next, we are going to be deriving a relation from Joule-Thomson coefficient. We are going to be deriving a relation of constant temperature coefficient. Constant temperature coefficient. Derive an equation for the constant temperature coefficient. We are going to be using enthalpy, because we know that enthalpy H to be equals to the function of temperature and pressure. So from our fundamentals of partial derivative, we can rewrite this. To be the H equal to the partial derivative of H over T, keeping P constant, dt, plus the partial derivative of H all over P, keeping T constant, dp. So this is what we have from our enthalpy, this is what we have. So next, we know that the partial derivative of H is equal to dp dt, that is the partial derivative of T. We can as well make dp the subject of this relation. We are going to have dp to be equal to we are going to have Cp to be equal to the partial derivative, that is, if we divide both sides by the partial derivative of T, we are going to be having Cp to be equal to the partial derivative of H over the partial derivative of T, keeping P constant. So this is what we have. So we are going to substituting this, which is equal to Cp, for the partial derivative of H over the partial derivative of T, keeping P constant in this equation. So if we do that, we're going to have H to be equal to Cp. By substituting the value of Cp, we are going to have Cp dt plus the H, that is the partial derivative of H over the partial derivative of P, keeping T constant, dp. All right, this is what we have. So next, we are going to be dividing both sides of this equation by dt. If we divide through this equation by dt, we are going to be having the H to be equal to, that is the H all over dt. We are dividing through by dt. We have the H all over dt to be equal to Cp dt all over dt plus the partial derivative of h all over the partial derivative of p, keeping t constant, dp all over the t. So this is what we have. So next we are going to be rewriting this equation as the h all over the t to be equal to Cp plus the partial derivative of h all over the partial derivative of p dp, whereby we have this term dividing the t. So to convert this term to multiplication, we are going to be having 1 all over the t. This is what we are going to have, 1 all over the t. We're going to have 1 all over the t here. So if we multiply, this will become the p all over the t. The p all over the t. This is what we have. So next, definition of Joule-Thomson coefficient. We said that enthalpy is constant. So if we set enthalpy, which is h, let's say the h is equal to 0 in this equation, it implies that this equation will become 0 all over the t. It will be equal to Cp plus the h, that is the partial derivative of h all over the partial derivative of p, keeping t constant, dp all over the t. Now, since we have 0 over the t, 0 over the t will give us 0. And because we are assuming that the h is equal to 0, it implies that we are going to be keeping h constant here. So this will be nothing but 0 equal to the partial equal. We are also going to be having the partial derivative of p over the partial derivative of t, keeping h constant because we say h is equal to 0, which is constant. So next, we are going to be taking Cp to the other side of this equation. It implies that Cp will be equal to, that is minus Cp, it crosses the equality sign, will be equal to the h, the partial derivative of h over the partial derivative of p, keeping t constant, into the partial derivative of p over the partial derivative of t, keeping h constant. So this is what we have. So next, we are going to be multiplying through this equation by minus. Partial derivative of h all over the partial derivative of p, keeping t constant, multiplied by the bracket of the partial derivative of p all over the partial derivative of t, keeping h constant. Keeping h constant. Now this is what we have. Now the partial derivative of h all over the partial derivative of p all over the partial derivative of t, keeping h constant, is equal to the Thomson equation, because we said that mu is equal to the partial derivative of p over the partial derivative of t, keeping p constant. So what we do is that we substitute the value of mu in this equation. It implies that Cp will be equal to minus mu into the partial derivative of h over the partial derivative of p, keeping t constant. This term here can be referred to as the constant temperature coefficient. So we can say the h all over the p, keeping t constant, is equals to the constant temperature temperature coefficient. So from the Joule-Thomson coefficient, we have been able to derive an equation for an ideal gas, whereby we saw that for an ideal gas, there is no change in temperature. For an ideal gas, there is no change in temperature. When we derive an equation for an ideal gas, we realize that there is no change in temperature. From the Joule-Thomson coefficient, we have also been able to derive the constant temperature coefficient, which is nothing but the partial derivative of H all over the partial derivative of P, keeping T constant. So these are the relations that can be derived from Joule-Thomson coefficient. Thank you for watching and stay tuned for more videos.